In this video, I want to talk about basic function operations. So this would be things like addition, subtraction, multiplication, and then if we have time in this video, we're going to talk about division. Division is the only one that gets a little more tricky, but it's not because the operation itself is hard, it's just that you have to be a little careful with things like domains. So if we have time in this video, we'll cover that, but if not, I'll make a separate video. But I want to cover all of the basic function operations that you might encounter. So um, um, if we have two functions, okay, let's say we have f of x. So let's let f of x and g of x be functions. Okay, then if we have f plus g of x, this is equal to f of x plus g of x. Okay, if we have f minus g of x, this is equal to f of x minus g of x. So this is exactly how you think it would be. If you have f times g of x, this gives us f of x times g of x. And then if we have f over g of x, this is f of x over g of x. But the only thing is here is we have to be a little careful with the domains here, okay? But other than that, we are good to go for all. These are all exactly how you would expect them to be, okay? So how about we have f of x equals 3x to the third and g of x equals x squared. We want to find f minus g of x. Okay, well, if we have f minus g of x, this is equal to f of x minus g of x, okay? And so all we have to do is substitute in what our values for f of x and g of x are, right? So this will give us 3x squared minus, 3x to the third minus x squared. And it should be noted that's probably about as simple as you're going to get that one. Okay. And very similarly, if we have f plus g of x, this is f of x plus g of x, which is going to just be the same thing. It's just now we're adding them. Okay. And I suppose if you want to simplify this, you could factor out an x squared. Just for fun, we'll do that. We'll have 3x plus 1. That's fine as well. But you get the idea, right? It doesn't. You could also stop at 3x to the third plus x squared. That's also fine. Okay. And then if we have f times g of x, I can do a little better with my multiplication symbol here. Let's f times g of x. Now we have f of x times g of x, and that's going to give us 3x to the third times x squared. Okay, and remember, if we multiply two variables together with exponents, all we have to do is add the exponents. So this is going to give us 3x to the 3 plus 2, which gives us 3x to the fifth. And that would be your answer here. Okay, now let's let a of x equal x squared plus 1 and b of x equal x minus 1. And we want to find a plus b of x. Okay, so this is equal to a of x plus b of x. Okay, so we have x squared plus 1 plus x minus 1. Okay, so we'll have x squared, okay, the 1 and the minus 1, those will cancel, so we'll have x squared plus x, and that would be our answer. You could also rewrite this as x times x plus 1 if we factor out an x here. Both of those are acceptable answers in my opinion. Okay, if we have a minus b of x, this is equal to a of x minus b of x, which is going to be equal to x squared plus 1 minus x minus 1. Okay, and now we have to be a little careful with our distribution of our negative sign here. So if we distribute the negative sign to the x and the negative 1, we'll have x squared plus 1 minus x plus 1 because we're subtracting a negative, so this becomes a positive. So really, we're going to end up with x squared minus x plus 2. Okay, x squared minus x plus 2. Okay, and that would be probably as simple as you're going to. I don't think we can factor that very easily. So, and then we have a times b of x. We'll have a of x times b of x, and that's going to give us x squared plus 1 times x minus 1. All we have to do here is FOIL. So if we do our first, we'll have x squared times x, which is going to give us x to the third. Then we'll have x squared times negative 1, so minus x squared. Then 1 times x gives us x, and 1 times negative 1 gives us negative 1. And that is actually, I think, as simple as we're going to get that. So we can go ahead and circle that and call our answer. Okay, now let's take a look at the quotient of two functions. So I mentioned that if we divide two functions, we have to be a little careful with the domain. That's really all that you have to be careful about here. So if we have p of x is equal to x squared, or sorry, x plus 2 times x minus 2, and q of x is equal to negative x minus 3. We want to find changes. I don't know why did f over g. We can do p over q of x. I guess this should be p over q as well. Okay. If we want to find p over q of x, let's first write that out. Okay. So if the numerator is going to be x plus 2 times x minus 2, and then in the denominator we're going to have negative x minus 3. So if we want to find the domain of this function, all we really have to do is find out what the excluded values are, like we did before. So what I was saying was a little tricky about these is unless you have in previous examples with addition, subtraction, and then multiplication, unless you have something that's going to introduce a variable in the denominator, you don't really have to worry about the domain changing a whole lot. Unless one of those functions has a really restricted domain. What's interesting here is you have two functions here that are defined on all of the real numbers. P of x is defined for any real number. There's no real issues with plugging any numbers in there. Q of x is defined for any real number. There's no issues with plugging anything in for Q of x. But now if we take P divided by Q, all of a sudden we have an issue. Okay? So we have to find the domain here. So our excluded values, we take negative x minus 3 and set it equal to 0. We have plus 3. I guess we can just add x and we can find that, I suppose. That's a good way to do it. Plus x, and that's going to give us x is equal to negative 3. So that's our excluded value. Okay, so that's write everything but the excluded value. So we're going to have the interval from negative infinity to negative 3 with a parentheses, union that with parentheses and negative 3 to infinity, and that is going to be our domain. Okay, so all of a sudden our domain has changed a little bit from what we were initially allowed to do, because before, for q of x, there was no issue with plugging in negative 3. If we plugged in negative 3, we would have negative 3 minus 3, which gives us 0, and that was fine. But now that we combine them together in a quotient, that is going to be an issue. Okay. Okay. How about if we have gamma of x is equal to x plus 5 times x minus 4, and phi of x is equal to 8x plus 7. These are just Greek letters. Don't get freaked out by the notation here. I got tired of writing regular letters, so we're trying some Greek letters here. Okay, so nothing changes. There's no major changes here. So, okay, now we want to find the domain of phi of x over gamma of x. Okay, so we'll have, first let's write phi of x over gamma of x. That's going to give us 8x plus 7 over x plus 5 times x minus 4. So what are our excluded values here? Well, our excluded values are going to be whatever is going to make either of these equal to 0. Okay, so that's going to give us negative 5 and positive 4 they're both excluded values here. So we have to write our domain in terms of those. So our domain is going to be the interval from negative infinity to negative 5, and we don't want to include that point, so we're going to use a parentheses, union with parentheses negative 5 to our next excluded value, which is 4. Parentheses there because we don't want that either. And then we're going to union that with the interval from 4 to infinity. Okay? So this is going to be our new domain. And remember, we didn't have any issues before. We had like gamma, there was no problem with plugging in -5 or 4 with gamma before. But now, because we have done the quotient, we have to be careful with the domain. So keep that in mind. Anytime you're doing a quotient of two functions, you have to be very careful with the domain of the function. Okay, and there's one last operation that I would like to do here really quickly, and that is something called the composition of two functions. This is like the one operation that doesn't really apply to regular numbers, but it does apply to functions. That is the composition. So you might see something that looks like f with a little circle g of x. Looks like fog of x, I guess you could say, if it's f with g. It kind of looks like a little O or a little circle in between them. This is just f of g of x. So before we saw variable inputs for functions, variable expressions as inputs. That's effectively what we're doing here. Okay, so don't be overly bothered by the notation here. So in this example, we have q of x is equal to x squared plus 5, and r of x is equal to the square root of x plus 3. So first we need to find q composed with r of x. So what this is going to be, it's q of r of x. Okay, so we're going to plug in r of x as an input for q of x. Okay, so we're going to have q of the square root of x plus 3. Okay, and then we're going to plug that in for our function q. So we're going to have the square root of x plus 3 squared plus 5. And remember, if you square a square root, it just simply undoes the square root sign. So this will become x plus 3 plus 5, and if we combine like terms, we'll end up with x plus 8. So our new function when we compose these two is x plus 8. Okay, and then now we have r of q of x. We do the other way. So if we do r of q of x, that'll be r of q of x. Okay, which gives us r of x squared plus 5. Okay, and then we have, with that, we have the square root of x squared plus 5 plus 3. And here we can just combine like terms, and we get the square root of x squared plus 8. And that's as much as we're going to be able to do here with this one. Okay, we can't simplify this any more than we already have it, so we're going to leave that alone. So what we notice is that if we have q composed with r of x, it is not equal to r composed with q of x. They're not the same thing. Okay, so it's kind of like division, right? If you can have a plus b is equal to b plus a, and you could have a times b is equal to b times a, but you can't have a divided by b is equal to b divided by a, or a minus b is equal to b minus a. So this is kind of like that. It's not necessarily something you can do interchangeably with the order here. Okay, so keep that in mind. You're going to see in in our next video probably, special instances when they are the same, but we'll talk about that here in a little bit. So let's do a of x is equal to x plus 1, and b of x is equal to 2x squared. We'll start with a composed with b of x. So this is a of b of x, which is going to give us a of 2x squared. So we can plug in 2x squared anywhere where we see x and a. So we're going to have 2x squared plus 1, and that's actually as simple as we're going to get that. Right? I don't think we can do any more to simplify that, so we're going to call that one good. Okay, and then b composed with a, we'll have, that's b of a of x, okay, which gives us 2 times, well, let's write this out a little better, b of x plus 1. So anywhere we see an x in b of x, we're going to plug in x plus 1. So we'll have 2 times x plus 1 squared. Okay, so we can write this out a little more. So we have 2 times x plus 1 times x plus 1, and we can FOIL this out. So we have 2 times x squared plus x plus 1. And now we can combine like terms, so we'll get 2 times x squared plus 2x plus 1. And if we distribute that 2, we're going to get 2x squared plus 4x plus 2. And that is about as simple as you're going to get that. Okay, so once again, notice these two are not the same.